recordings proved to be helpful. I always thought that it's going to be a good idea to kind of have a way to go back. So, as said, we're going to deal today with the one-way. I'm not seeing myself on the screen. Hi, Madeline. Okay. Okay, so today we're dealing with a one-way between groups and over. And basically when we go back now, so we have talked about the normal distribution curve, we've talked about the set distribution. We've talked about the t-distribution that basically means to estimate the overall distribution and variability in the population based on the variability in the sample. And I have it here. Okay. So now we're coming to F distribution. And the F distribution is a unimodal, right skewed or positively skewed distribution, which we will use to test against our hypothesis of an ANOVA. Basically, we will get to what this null hypothesis is, just take it in as it is, as I'm explaining it now. It's a unimodal, right skewed to the positive, so from your end in that direction, distribution with one critical value. So we will only do this as a one-tailed hypothesis, and we will test against the null hypothesis that one of these groups will be different from another. So essentially, you're using the F distribution only when you work with 3 or more groups. Yes. Okay. So we're working with 3 or more groups, and it's used when you have nominal independent variables that basically define groups, just like we had with the t-test, where we had cheap wine versus expensive wine, or whatever other group you could think of, and the scale-dependent variable. So the example, when does your question fit?
No, I just didn't want to interrupt you.
That's fine.
So if it's only one critical value set, like the different values of the speed that it's like that, right?
It's positive skewed is like it has a long tail, and somewhere on the tail is your critical value.
On the critical value, is it on the left side or is it
on the right side? It's right skewed. So the tail goes to the right. We will see. So there's a specific, and you have that on Canvas. So we have today 4 files on Canvas. We have the 2 chapter lectures. We have a spreadsheet, and we have the F-score table. And that F-score table shows already what I was describing was the distribution. So basically, the example that Nolan and Heinz are showing here now is one of these examples where you basically have 3 or more independent variables or levels of one independent variable. That's always important. It's one independent variable, but it's different levels of one independent variable. So remember when you go back, and there was a question we discussed in class, where we had is California king bed size, is this an ordinal variable or is this a quantitative variable? So we had, you remember, we had the king size and king size, queen size, California size bed. The bed sizes were the actually ordinal variable because they were ordered and they were reflecting an order. So if that would be an independent variable, that would be the 4 groups of bed, and that would be an ordinal variable. So that would be a definition of a group. Whereas the count of how many people actually bought the respective size, that would be here the dependent variable. So that would be here depicted on the y-axis. As an example, the distinction between a categorical variable and a continuous variable. So the example that Nolan and Heinz are showing here is the likelihood of a collision while merging onto a street. And there are 4 different, 4 different conditions. We have a drive-alone condition, we have a passenger condition, we have a video phone condition, or a cell phone condition. So we have with the drive-alone condition, we have the smallest likelihood or risk of a collision. It increases when we have a passenger. No idea why that is the case, but probably the conversation with your passenger. Then you have a video phone condition, and then you have a cell phone condition. I have no idea whether a video phone condition would be less dangerous than a cell phone condition, but that's the example. Probably if we read up on that paper, so there's usually always a reference to the actual data. And they usually use real life data. Probably this will explain why there's a difference. But just this is to be seen as an example when ANOVA would be a suitable test to use. So if you want to compare now these different conditions, or you want to compare whether video phone is actually significantly different from cell phone, or cell phone is significantly different from driving, you could do that. You could find out what the differences are. You could do this by doing individual t-tests, comparing, or individual tests, comparing each of these conditions amongst each other. Why would you not do that? Could you think of a reason why this would not be a good idea? Where's my mouse? Okay. Why could it not be a good idea? Think about it. You have with every hypothesis test, you have a type 1 error. You have a possibility that you're rejecting the null hypothesis that these two groups are not different, but you're rejecting something that you shouldn't have rejected, or because they're actually identical, they're similar. So this type 1 error, we are usually setting at 5%. That's our 5%. So you have, if you do that 4 times, or if you have multiple comparisons, if you compare each of these groups individually, so you have 1 comparison, 2 comparisons, 3 comparisons, then you have to compare this versus this and this. So it's multiple comparison. With each time, you accept a type 1 error risk of 5%. So what happens if you do that? You're essentially creating a risk that is essentially 0.05 each time. So it's 0.05, 0.05 each time. You're doing that with, let's say, 3 comparisons at the very least. So you essentially, you have a 5% risk to the power of 3. But it's not only that, it's essentially, if you want to be right in not rejecting it, it's essentially coming down to 1 minus that risk. Only then you're right, right? So the 95% you're right. In 95% of your confidence interval, you're right to accept the null hypothesis. That gives you this. This gives you an 85% probability that you're right. So if you have a dichotomous outcome, you have 5% and you have 95% of being right. So 1 minus your probability that you're not right to the power of 3 gets you to your probability that you're right. The problem with that is that you have, and the probability of 100% is either you're right or not, you're not right. The probability of not being right is 1 minus this. So now your acceptable probability of accepting an error inflates now to 14%. Because you have each time 5%. Yeah?
Well, I think before you do it, are you able to click on the equation that's on this, like what the formula is?
So you have, when you accept the 5% risk,
Yeah.
that you make a mistake, you want to quantify the probability of being right.
So why do you raise it to the power of 3 instead of multiplying by 3?
It's the same thing. Okay. Okay, let's do this. 0.05 equals 0.05 multiplied by 0.05.
No, I know that. I mean,
Oh.
instead of doing 0.05 times 3. why are you doing 0.25 and 0.05 and 0.05?
Because it's mutually exclusive events.
Uh,
It's different groups. Each time is a separate event. So each comparison is individually, each hypothesis test that you would do for comparing these conditions, they're independent samples.
What are the exact examples? Let's say you just want to compare like driving alone to driving with a phone.
Mhm.
That's just one t-test.
That is one. If you're just interested in these two conditions, then you can just go ahead and do this one comparison. But if you want to understand, are these conditions inherently different? Are there differences between these conditions? Just as a general understanding, you would do that. You would take an overarching test, and the ANOVA does exactly that. The ANOVA, the null hypothesis of an ANOVA is that one of these groups is significantly different from the other. That's the research question. So none of these, and so the null hypothesis would be none of these groups mean or estimate is different from any other group's means or estimate. So back to that. So you basically, you have now 5%, which gives you a 95% probability you're right. This to the power of 3 gives you an 85% probability to be right. 1 minus that probability of being right, that's your type 1 error risk. And this is even worse so. This becomes even worse when you inflate. Let's say we have now an increase of comparisons. So the more groups you have, now that's actually the next slide shows you exactly that what I'm calculating now. With every time, with every comparison you add to your grouping, this is increasing, tremendously increasing. This is not just a linear increase. This is actually virtually an exponential increase because it's a nonlinear increase. So that emphasizes what great problem that actually is and why this is so important. And this is exactly that graph here, meaning to show you exactly that simulation. So they're actually carrying this even further because if you have, this is not even the number of groups, this is the number of comparisons. Because if you have 3 groups, you're doing 3 comparisons, but if you have 4 groups, you do 6 comparisons. So it's also that the number of comparisons increases, and in the same fashion, the number of the probability of a type 1 error increases. So that's a substantial increase. So essentially, when you look at 7 means at 21 comparisons, you actually have a higher risk of a type 1 error than not having type 1 error. Yes.
I understand like mathematically why the probability of type 1 error increases, but not conceptually.
Well, you're drawing random samples, right? You're drawing random samples, so you have a certain risk that you, by coincidence, just drew a sample from an area of that population distribution curve that was just different.
Okay.
And then you see a type 1 error that's actually inherently not true because the variability was wide and it actually should have been not rejected. Yeah? Any questions to any of that? Or is it clear? I think it's clear as a simple principle, right? You have 5% risk with one comparison, and you have just a substantially higher risk with more comparisons. Because every comparison is a mutually exclusive event. So now you have in the simplest approach, yeah, so then the Swiss Army knife comparison, I'm not really sure I'm following, but basically what you have, what they mean to say is like you have with a SAT and the one sample t-test, you have a very simple comparison. If you have more of these different tools in the Swiss Army knife, it's getting more complicated. Then you come in the realm of a sample comparison with the t-test. And the more groups you have, the more complicated and the more complex it gets. And the F distribution basically helps you to get like a guiding star whether these means are actually different to some extent. So it's in its conceptual principle, how it's being used, You will always use, if you have more than, if you have 3 groups or more, you will always use an ANOVA. And if the ANOVA shows that you should be rejecting the null hypothesis of an ANOVA, the conclusion is that there's at least 2 pairs or 1 pair, 2 groups are significantly different. And then you do something that is called post hoc testing. Hoc is Latin, so post is clear, right? But hoc is Latin for an event. So it's post-event testing. So it means you did the event of doing an ANOVA. And what you do after the ANOVA is post-hoc testing, where basically you compare those groups individually with restrictions on what you will accept as significant. This is what we do at the end of this lecture. And there are methods to doing that. Good. Underlying hypothesis, this is important. It needs to be randomly sampled, they need to be independent, and they need to be normally distributed, as all the tests we're doing in this class. So they are and so then we are only doing so-called parametric tests. Parametric tests have as the underlying assumption that the distribution is normally distributed. Non-parametric tests do not make these assumptions. Okay, once again, this is the bird's eye view. This table conveys the bird's eye view. We have one sample where mu and sigma are known. You will think set distribution. With a one sample where only the mean is known, only the mu is known. You will do a t distribution. You will utilize a t distribution. You basically use this in the same way as a set distribution with large sample sizes. So you remember the t-score table basically converges towards being at the same critical values as the set distribution. So as soon as you add 500, set and t is the same. So we remember the type 1 error of 5%, there was 1.96 for the set distribution and 1.96 was 500 sample size for the t distribution. In real life, statisticians kind of let you get away with using a set distribution as soon as you surpassed a sample size of 30, but that's a practical comment. Good. So you have one sample, only the mu is known, that's a single sample or one sample t-test. And we have 2 samples, depending chronological order, non-chronological order. It's a paired sample t-test if it's the same participant, or it's independent sample t-test if it's independent groups, independent samples. If you have 3 or more, what can be used with 2 samples, you would think of an ANOVA. Yeah, link some of distributions, yes. So you're linking here the t distributions together, and you merge them into one hypothesis. So it's in principle, it's done in a quite simple format. You're calculating a so-called F, and you're comparing this against the F distribution. So the F distribution, as said, is a unimodal distribution shown in that score table that I have provided to you in Canvas. That's the distribution. Unimodal, right skewed or positively skewed. You have one critical F value, which you just will need to know how to read it from the table. It's not terrible, looks worse than it is. Follows a very simple principle. But your type 1 error is contained here in the tail beyond your F distribution or your critical F. So you will find the corresponding F value as soon as your F score is exceeding that critical F. You're rejecting the null hypothesis, and you're saying that at least one pair is different. So one group is significantly different from any other group, but you cannot see which one is different from which one. For that, you need to do post hoc testing. Yes.
You answered my question.
Okay. Any other questions? Easy, right? Good. Then let's get to the fun part. So how do you calculate this F? So you basically, you remember what the variance is. You know that the variance is the deviation of each individual score from the mean. Squaring this deviation will get you, when summing it up, to the sum of squares. Dividing it by your degrees of freedom will get you to the variance. So now if you have, and this is where it's getting tricky, so you have now groups. So you have a variance within those groups. And these are basically what you need to take into account, because you have a variance within groups and you have a variance between those groups, between the means of these groups. And the picture that Nolan and Heinzen have that actually shows this the best is, for some interesting reason, it's only coming very late. So basically it looks like that. So forget the example. I will introduce the example in a second. But you basically have four groups of four different means. There are four different variances. If you create a mean, if you calculate a mean between means, you get one grand mean. That's actually, that's a term, grand mean. That's the mean of means. So now you have, not only do you have variance within the groups, you also have variances between the means, between the groups. So if you have now four means, these four means create variance because they deviate from the grand mean. So the distance from here to here, from here to here, from here to here, from here to here, creates a variance, creates a variability between those groups. So you merge those together and you basically calculate an F, which has a critical threshold, which you utilize for hypothesis testing. And if this F, this calculated F, exceeds that critical value, you're rejecting your null hypothesis. And just compute that at least one group is different from another group. Yes?
Are you able to explain how you find the variance? What does it mean within and then?
Okay, good point. Okay, so let's take that example here, foraging. So you have here four data points within your group. That's 4 rows in an Excel spreadsheet. You calculate the mean, and then you calculate from each individual score, you subtract the mean, gets you a deviation. These 4 deviations you square up, you add up, gets you the sum of squares for that particular group. Dividing it by the degrees of freedom of that group, which is 4 minus 1, is 3, gets you to the variance within that group, just within that one group. But you have 4 of those. And now you do the same thing. You have a grand mean, so that's these 4 means summed up and divided by 4 gets you the grand mean. That's the mean of means.
So that's for mean, not for variance.
No, that was variance. We're only dealing with variance. So the F is calculated only by taking, paying attention to the variance. So the F is essentially a ratio between the variance between the groups. So that's the variance between the means and the variance within the group, amalgamating all the variances you see in each of those groups.
How do you, I understand how you find the variance within, but how do you do it between different groups?
Well, you have 4 entries, but you have 4 means.
Oh, so you just would do like 1 minus the other one.
No, you do, you sum up, you get a mean of means, you get the grand mean, that's the mean of these 4 means. And now you basically calculate each individual mean of these 4 means that you have. You calculate a difference, a deviation. Mean 1 minus grand mean, mean 2 minus grand mean. That gets you the deviations. Squaring that up gets you to the sum of squares, dividing it by the degrees of freedom of the groups, which is now 4 minus 1, because it's 4 groups in our society example, gets you, divide that by 3, you get to the sum of squares. And that's, no, wrong, gets you to the variance. And that's your variance between groups. And then you divide the variance between groups by the variance within the groups, and you're at an F. And that you utilize to test, to interpret your statistic, your F statistic. So it's the difference among the sample means divided by the average of the sample variances. Good. Any other questions to this? I know it's a little rough, but once you have the concept, it's a straightforward path. And we will do the examples. You will see it becomes clearer once we do the example. So types of variance. So these analysis of variance, you have two different approaches. You have a between groups approach, which is basically an independent sample t-test over all the groups. It's independent samples. They're absolutely independent from each other. They're different participants. And then you have a within groups approach, and that's chapter 13. The within groups approach, you have repeated observations for each individual or for each society, for each group. So let's say you have the example we had before with the likelihood of a collision. That would be if you are testing individuals in different conditions. So it's like there's Miss Smith is driving, Mr. Doe is driving, and Mr. Miller is driving. You have them under 4 different conditions. That would be a within groups example. So you will use an ANOVA to compare these 4 groups, taking into account that each individual per se contributes and has contributes to the variability of the group, because the driving skills between certain individuals are different. So this will reduce the variability between the conditions, between the levels of your independent variable. Okay, so between groups and the within groups ANOVA. So that's why it's called a one-way between groups ANOVA, because it's a one-way, meaning it's one variable, one scale variable in 4 different groups. A one-way within groups ANOVA would be one scale variable, different groups, but same individuals going through the same 4 different groups, those 4 different levels of the independent variable. This can obviously be altered. This is, by the way, this is also called a repeated measures ANOVA. So sometimes you see the synonym. It's the same thing. What is to be kept in mind? A one-way ANOVA is because there's one scaled variable. If you measure in a second or a third or a 4th variable, you get to a 2-way, 3-way, 4-way between groups or within groups ANOVA. And the two-way between groups ANOVA is chapter 14, which will not be part of quizzes and exam. I provided a PowerPoint, but I think if you have a solid understanding of a one-way between groups and the one-way within groups, I think the objective of this class is done. Good, we can talk about it in a separate session if somebody's interested. Okay, so one-way means we have one nominal variable with more than 2 levels and the scale dependent variable. So more than 2 levels implies it's 3 or more. Between groups, more than 2 samples with different participants in each level, just as we just discussed. Okay, hypothesis test of within groups, same participant goes through different levels. Any questions on this? Then let's move on to the assumptions. So I mentioned them earlier already. So it's a random selection of samples. So these need to be randomly sampled from a population, otherwise you have a biased sample, which would be a problem by its own right. So for example, if you have ordinal variable, if you have an ordinal variable and you have like, let's say you stratify as per quartiles, for example, and you have 4 different groups and you know they're different for one particular feature, you would not compare this feature because it's nonsensical to do that. So it needs to be a random selection of samples and not a specific selection from different specific area, a specific numerical value. It needs to be normally distributed. That's the assumption of the ANOVA. If you would do a non-parametric ANOVA, it's not called ANOVA then, it's a so-called Kruskal-Wallis test. different part of your education. Homoscedasticity. That's the interesting one. Homoscedasticity. Homo means same. Scedasticity refers to the variability. That means that the variability between these groups, so the variances within these groups, should not differ by more than, I believe it was 20%. So the variance should be somewhat equal between those groups. Because if you have one group that has like this tremendous differences, and you have the other groups basically have like small differences, that one group will basically inflate your denominator, and will consequently wrongly lower your F, thereby increasing your chance of a type 2 error in your ANOVA. So that's why homoscedasticity is important. I'm flagging this word because it's quite a complex word. I understand that. It's pronounced homoscedasticity, and try to memorize it, because the opposite of homo is hetero, so it's heteroscedasticity. Heteroscedasticity means there's differences between those groups. Homo and heteroscedasticity will be super important in the context of regression, because one of the assumptions that a regression makes that there is homoscedasticity and that there is no skewness of the variability, meaning it's gonna change, and in higher levels you have much more variance. That would be a violation of the principle of homoscedasticity for regression. So that's an important topic. Okay, again, 3 assumptions: random selection of the samples, no biases, normally distributed sample, and homoscedasticity. Any questions on either of these assumptions? No? All right. The 6 steps of hypothesis testing, same principle again. So we're identifying the populations. We know who, so we're talking now specifically about the one-way between groups and over. We need to understand the populations we're dealing with. We need to understand what distribution do they have. So that's when we're quantifying the standard deviation, where we're quantifying the means, where we also state our assumptions, which is random selection, homoscedasticity, and normal distribution for the ANOVA. Then we have a null and a research hypothesis, where the null hypothesis is that none of these groups is different from each other. Research hypothesis, at least one mean is significantly different from another mean. That's the research hypothesis. Then we determine the characteristics of the comparison distribution, which we know is a unimodal right-shaped distribution that we're basically comparing against by calculating our F statistic. We also determine our critical F, which will basically be our cutoff value. If we're exceeding that in the computation of our F, we will reject the null hypothesis. We're calculating the test statistic. This is when we're calculating the F, which is variance between groups divided by variance within groups. Keep in mind that likely between those means you have more variability as within the groups. So it's the larger value. So the numerator is going to be larger. That's kind of a memory helper, how you can remember what's between, what's within. And once you calculate the test statistics, you know the F, and then based on the F, you can make, in the knowledge of a critical F, you can make a decision. That's essentially all that is. It's computationally, it's a little bit more complicated. And we will now go through the calculations of that. And it's not terribly hard, but basically we will do this now on our example 12.1. So that's in the Excel spreadsheet. And we have the 4 populations. The example essentially is the following. So 12.1, it's on Canvas. So it's the spreadsheet. You have 3 spreadsheets in your worksheet. And 12.1 is the one-way between groups. Okay, so research is basically so this is an actual experiment. It's a subset of this actual experiment. I hope they did it in a larger sample size than that. But basically, they went to different populations, and they had in this experiment these different societies. So participants from different societies play the so-called dictator game. So the dictator game, two players are given a sum of money equal to approximately the daily minimum wage for that society. The first player could keep all the money or give any portion of it to the other person. The proportion of money given to the second player constituted the measure of fairness. For example, it would be considered fairer to give the second player 40% of the money than to give him only 10% of the money. So now what do we see? So we see now our four different societies. So we have foraging, farming, natural resources, and is industrial. So foraging, so they're basically like hunters and gatherers. Then they have farming, the more advanced version of that. And then we have natural resources that basically have this more systematically organized in agricultural way, in an agricultural way, and then we have industrial society as the fourth group. So what we see already with the naked eye is like somewhere there is like the break. So we will quantify first. So this is a mean. So we take an average of these four and participants. We're calculating, we can do this with an average of that. That basically makes it fairly simple to kind of calculate those four estimates. And we see that somewhat here, we kind of are at a rather higher fairness level as compared to foraging and farming. So I should do the attendance at the end of the class. Okay, so we're looking at these four different groups, and we're having now our null hypothesis phrased as if one mean is different from any other mean, this would basically be rejecting the null hypothesis, which states that on average they all have the same fairness behavior. And the research hypothesis, they do not all exhibit the very same behavior. So that's simple, right? So now first we need to quantify the degrees of freedom, and there are 2 degrees of freedom that we need to calculate our variances, and that's the degree of freedom of between, which is the number of groups, and the degrees of freedom within. And the degrees of freedom within are the degrees of freedom of each individual group summed up. Or alternatively, it's the sum of all individual scores minus the number of groups, comes to the same thing. So, and that's what they mean to refer here. So if there are 3 levels of the independent variables, we have 3 levels, that's 3 groups, minus 1 is 2. If there are a total of 20 participants in each of these 3 levels, it basically comes down to this. So you have 20 in total, minus the number of groups will lead you to degrees of freedom within. It's the same as summing up the individual degrees of freedom, but that's logically. Good. Now we have a couple of steps that we need. So we have, okay, let's do this first. So we have now our ANOVA table. So we want to determine our critical value. So we have 4 groups, and we have a total of, so we have degrees of freedom between is 4 minus 1, right? 4 minus 1, that's 3. Then we have degrees of freedom within, that is with 4 entries here, we have 3 here, 3 here, 3 here. That's 4, 7, 10, and 13 minus 4 groups. That's 13 minus 1. That's 9.
Oh, this is for degrees of freedom.
This is just degrees of freedom now. So we have now 3 and 9. So 3 and 9. So if we click now on our F-score table, so we have in the numerator is degrees of freedom between. So our degrees of freedom between is 3. Within, we have 13 minus 4, that's 9. So we're going down to that column of 3, and we're going all the way down until we have wrong. Oh, sorry. So we're going to 3 in the denominator, and we're going, no. Okay. We have numerator here. Within groups, degrees of freedom, that's the denominator, and we need 3 on the numerator. So we have 3 groups. We have 3 groups in the numerator. We have 9 in the denominator. Okay. Okay, so we have in the numerator within between groups, we have 3 with 4 minus 1. It's 4 groups minus 1. That is the redundant that we dropped. So we have degrees of freedom of 3. We have 13 minus 4 for 4 groups, gets us to the degrees of freedom within. Gets us here where 3 and 9 are coming together. Add an acceptable type 1 error rate alpha of 5%, gets us to 3.86.
How do you know that that's 9?
Well, yeah.
So, like, how do you
So
know
these blocks, okay, let's start from scratch. Okay, so we have here blocks from blocks of degrees of freedom in the numerator. That's the between groups degrees of freedom. And then we have blocks of degrees of freedom in the denominator, which is here 1, 2, 3, 4, 5. So if we have degrees of freedom in the numerator of 3 and degrees of freedom in the denominator of 9, we need to go down to 9 and stay in the column of degrees of freedom in the numerator. So that's 3.86.
I'm saying, how do you know that it's 3.86? There's the whole column. How do you know 9 is like?
Because here's the corresponding P. That's 5%. So you set your critical value again at 5%. That's the alpha. That's the alpha for a t-test, for an ANOVA.
If our alpha was 0.025, then we would choose.
Exactly. If you would set this at 2.5%, your critical F would be 5.08. Yeah. Okay, so that's our critical F. 3.86. So now we need to calculate this somehow. And that is done. So again, so this is the F distribution. So this is the distribution of F as we are expecting it based on the distribution of our comparison. So we know that 3.86, that's our critical F. Everything beyond that would be a significantly different, significantly different from the null hypothesis, and that would imply that at least one of these groups differs from one of the other group means. So now we have the logic is between groups variability divided by within groups variability. So it quantifies the overlap of these different groups. And it basically, this becomes your distribution. So it basically amalgamates all these overlaps between the variability of all this normal distribution of each group and quantifies that, and then either rejects or does not reject the null hypothesis of these overlapping to an extent that renders them to come from the same distribution. So 2 ways to estimate that we discussed. And this is really here the logic. So we talked about this, and this is really how you have to look at this. And with the overlap, you can guess it already to some extent. So if here the variability would be as wide that they would overlap, and they would overlap the grand mean, then they would by definition not be significantly different. But if these are small enough, which is essentially constituting your denominator, your f will automatically be larger. So if the differences between the group means that are in the numerator are large, but the within groups variability is small, and there's less overlap between the variability of these groups, of these distribution curves of the individual groups, then you're more likely to reject the null hypothesis of at least one being different. Make sense? Yeah. So to finalize now what you see, you put your insights into a so-called ANOVA table. Those of you that have looked at the homework already, they will know that's homework 3. So the ANOVA source table essentially is a table that follows a very comparable outline always. And you will see that source table from R, computed by R. You will see one here from SPSS. You will see various of these source tables. And they always look the same way, because these are the mainstays and the main information pieces from an ANOVA. The source table actually means to summarize these and give you an overview of what you're actually looking at. And it looks like that. So you have here on the very left, in the first column, you have a source, which is either between or within or total. You have then the sum of squares. The sum of squares we know, so it's for sum of squares between, it's the grand mean, and then it's each individual mean minus the grand mean. This gives you your deviations. This squared gives you your squared deviations, and that added up gives you the sum of squares. Gives you the sum of squares between. If you do that for all your individuals, all your individual scores gets your sum of squares within, and then putting these all together becomes the sum of squares total. So now sum of squares total, and this is important to keep in mind, because sum of squares total is basically a sum of squares between and sum of squares within. So this sums up to sum of squares total. So there's an arithmetic association between each of these components, because then you go to the degrees of freedom. So degrees of freedom between and degrees of freedom within. We talked about between. For our 4 societies, that's 4 minus 1, 3. Now we have degrees of freedom within, that's 13 minus 4 for 4 groups, that's 9. Degrees of freedom total is the sum of degrees of freedom between and degrees of freedom within. So that would be, in our case, would be 12. Now we're coming here to a mean squared error. That's essentially is, So this is a mean squared error. So this is basically a mean sum of squares, so to say. It's comparable to a variance. So that's our variance now. So we have mean squared error is basically the sum of squares between divided by the degrees of freedom between. The mean squared error within is sum of squares within divided by degrees of freedom within. The F, and this is now where the variance kicks in. So it's MS is essentially, it is the variance, nothing else but the variance. So the F is now your MS between divided by your MS within. So that's your variance between and your variance within. They label it different, and they don't label it as variance because they want to prevent you from thinking as a variance that you would need to calculate was the degree, dividing it by the degrees of freedom like we did. So now we have variance between and the variance within, and we get to the F. So just understand the arithmetic dependencies of all these different parts of this. Make sense? Yeah, it's not terrible. It's not too complicated. So the ANOVA analyzes three different types of statistical deviations: the deviations between the groups and the deviations within the groups and the total deviations. The total deviations are basically something to be quantified quite simply. And this is how we're going to do this. So you basically, you have here, you have three forms of deviations. You have your total deviations, and the total deviations are basically each individual entry minus the grand mean. You have the within group sum of squares, which is basically the x minus the individual group mean. And you have lastly, we're getting to this. So then you have the between groups sum of squares, which is basically the each individual mean for each score from the individual grand mean. We will do that in a second. Okay, so let's go to what it essentially means and how you calculate this. So it's simple. The only thing you need to do, you need to bring your data now from a wide format into a long format. And this is simply done by calculating and transposing it, as we've done in the past. You're just bringing it in the same format, and that's foraging. That is farming. Then we have here the last three for natural resources. Then you have natural resources here as the next one. And then you have lastly, you have industrial. So manage that. Screw that one up. 28, 32, 33, 40, 47, 43. Just closing this down. Okay, so this is industrial. So once you have your data in this format, you basically can quite easily now calculate your grand mean by basically just calculating the average of all these entries. That essentially will be 40, 47, 49, that will be 39.38. So this is our grand mean. So to get our sum of square total, so these are the individual x. So now we want to calculate x minus grand mean, which is now essentially this minus our individual entry. Which we just need to square. that should get us to a sum that is basically now our total sum of square of 629.1. So just again, so the only thing you need to do, which is the annoying part of this, you basically need to transpose it from a wide format to a long format, and then calculate individual scores from your grand mean. So this is x minus grand mean squared. So these are your squared deviations, and this is the total sum of square. That's your total sum of squares that you will be using moving forward. 629. So now there's an additional parameter that you will need, which is now your sample mean. And this is where you shift this a little bit to the right, because that's the sum of squares. You need a group mean. This group mean is the sample mean. And this is a little bit tedious because you need to create averages for each of these groups. So you get, for foraging, you get here 33.25. And now you need to calculate this down, and you need to basically put a placeholder for each of those, because you need to preserve your degrees of freedom for the calculation of the variance, right? So you need to propagate them down that you still have the same sample size for your calculations. So calculating this now for all your 4 groups, 35, and you have the average of this, basically gets you now to this point. You can just paste values. Yeah, paste values. If you have a situation like that where you're calculating average and you basically want to propagate only the value for the following 2 cells without shifting the formula, because if you would copy now only this formula down, you get here 45 and 46, but it should be the same value, and you want to preserve this value for the following cells. You can do this by selecting where you want the value to go, and you click here on the sides. This always gives you a paste special, and you can here select paste values. Paste values basically will propagate now this formula down. What is it for the second one? So this is how you propagate your means from each of these groups down. So that's your sample means. And we do the last one. That's not 44 and 44. And now you're basically ready for the next step, because now you want to calculate your individual scores minus the means, the sample means. So if you do now next, you do x minus m squared, you basically calculate this minus this in a parentheses. And now you don't need to log anything in because your reference cell is already in one row, one column for all the rows. Squaring this up basically gets you all the way here. That's your within SS. That is now the sum of this. It's 167. And now lastly, what you're calculating now is, Norn and Heinz do only, so they're doing this step, they're doing x minus m. They calculate the x minus gm. So they're not doing this step in between, because hypothetically, what you would also need to do is to calculate the between variability, the variance between, right? So they only do that arithmetically by basically calculating the difference between this one and this one. So you can also calculate this within between groups variance by calculating m minus gm squared gets you basically to equals this, this sample mean minus the grand mean squared gets you basically to your between groups variance. That doesn't look right. Oh. The login minus H27. So as you can see now already with the naked eye, if you look at it, so this is between groups. So Nolan and Heinzen, so this is the calculation of this. So you have here an individual X of all your entries minus your grand mean. If you square that, this gets you to your total sum of squares. If you calculate X minus the sample mean for each entry, you need to repeat the calculation as you need to place that entry of that group mean in that calculation, and you do X minus M squared. This gets you to the within group sum of squares. If you do M minus GM for the exact number of entries for each individual score, this sums up to the between groups variance, or sum of squares, sorry, not variance yet. So there's also an arithmetic dependency logically between that and that. So sum of squares can also be calculated by just adding up within groups and between groups, sum of squares, right? So that comes to the same value. And that's essentially what I meant was if you look at an ANOVA table and you have here the so-called source table. So you have here between, you have within, and you have total. You basically have with your sum of squares, you have between equals this 461. You have within, you have 167. And this comes back to what I said, the between groups variability is always going to be larger because it's individual means. These will be different than the variability you quantify within the group. But what is important to keep in mind is that these are arithmetically interrelated, and this total sum of squares needs to be 629. And this arithmetic dependency is quite important. Excuse me. This is important, and it's important to keep in mind, and will also be part of homework 3. So make sure you understand the calculation and each of those steps, how you get to each of these values. So again, you have an X, you have an individual score. You get from your groups, you get to a sample mean. And then the only important thing you need to understand is how do I calculate my sum of squares? You have a total sum of squares calculated by each individual X minus that grand mean, which is basically the mean of all of these, squared. Then you have X minus the individual group mean. That's your within groups variability. That's your adding up for all of these individual differences from their respective group means. And then lastly, you have M minus the grand mean, where you take the individual group mean minus the grand mean, and you square that variability up, and that becomes between groups sum of squares. So from now on, it's simple, right? So now the last thing we need is degrees of freedom. And we know degrees of freedom between 4 groups minus 1 is 3. Within, we have 13 entries. Now we have written it down here already. 13 entries minus 1 is minus 4 for 4 groups, right? Is 9. Logically, the sum of 9 and 3 is 12, right? But what we want to calculate now next is our mean squared error, which is essentially our variance. And the variance is calculated just like it was in a sample statistic as the sum of squares divided by the degrees of freedom. And that's how simple it is. So you calculate MS as the sum of squares between divided by your degrees of freedom. So you have a within groups variance of 18.6. Between the total MS, forget about that. You don't really need that, but it's basically 52. But you can leave that out because that's non-informative. And then lastly, you just need to calculate your F. And your F is nothing else but your between groups variance divided by your within groups variance. And this comes to an F of 8.27. And 8.27, if you remember our critical F, is significantly different. So that means at least one of these groups is different from another. I know it's arithmetically quite a bit. I'm well aware. I'm well aware. That's why just take this in. Go again through each of these steps. It's fairly logical. You really just need to understand what is the sum of squares, what do I subtract from what, and what does it mean? And these calculations that I've done here and shown you basically just leads to this source table. And this is really where the money is. This is really what needs to be understood. Because these steps in between, statistical software is doing for you, in most cases. But it's important that you conceptually understand what do these different components mean. So Norton and Heinzen walk you here through the same calculations as I've just done in Excel. I think it's worthwhile that you go through each of these calculations in Excel. I will post a spreadsheet as usual. It's just important to understand what's the meaning of all of this. So you have the sum of squares between, that's the M minus the GM. That was the last one we calculated. Then we had the sum of squares within, which is the X minus each individual M. And then we have the sum of squares total, which is X minus the GM. So we're calculating this now, we get to 827. So we are basically rejecting the null hypothesis. Based on that, we would go in the next steps to calculate the R squared, which is essentially considered to be the fraction, the proportion of the sum of squares between as a fraction of the sum of squares total. So that means that what part of that variance, of the total variance, is explained by the variance between the groups. And this is the sum of squares between divided by the sum of squares total. And this gives you an effect size for your ANOVA. So if you calculate here sum of squares total, no, sum of squares between divided by the sum of squares total, that gives you an effect size of how much these differences contributes to the overall variability. And the larger that is, the quote unquote more effect you will see. And the conventions here are different in Cohen's convention for two-sample t-test. But basically, they follow the same outline. So we have 0.1 to 0.6 is small, 0.6 to 0.14 is medium, greater than 0.14 is large. All right, post hoc testing next time, because now we know it's significantly different. Now we want to know which groups differ from which group. All right, thank you.
Yeah.